Okay, for the next number that we're going to do up here, it's Amazing Grace. Oh, where's my guitar? Damn. Oh well.
Bagpipes are better with that song.
I'm sorry?
Bagpipes are better with that song.
So we talked about the OSI model. So again, the thing to think about with the OSI model is the reason that we have it is for interoperability. You can go down and you can say, I want to take out my 100 megabit network interface card. I want to drop in a 1 gig card or a 10 gig card. And the moment that you drop that in, it'll start working because of the interoperability of dropping that card where it fits in the OSI model. The folks who built the card know the model and they know how to translate that information from the wire and bring it back up and add it into the rest of your network. So that's really why the OSI model was developed for us, so that we could actually do this interoperability of things to do. So as we saw this, the data travels down. We keep adding on headers and footers. We go across the wire. As we start coming up the other side, we're stripping this off the outside because all we care about, the reality of all we care about is the data. We just want to see that data. So in comparing both the TCP/IP model and the OSI model, over on the left-hand side, we see the suite of protocols. In the middle, we see the TCP/IP model, and on the right-hand side, the OSI model. So as we compare the OSI and the TCP/IP, you will see that TCP/IP has 4 layers in it. The application layer includes for us the application presentation and session. Transport is still the transport. The network is called the internet. And this used to be just the only layer we had at the bottom was the network interface, but they split that out so that we could have a little bit more of that interoperability. What's important are the different protocols that we have over here. We talked about the fact that the transport layer here in the middle, we've got TCP and UDP. At the internet layer, we've got IP and its associated add-on of IPsec. Now, IPsec was added on to IPv4 because when IPv4 came about, it was only there for connectivity. Security was an afterthought. All we cared about was connecting from one base to another, so IPsec was an add-on. As we take a look at layer 2, you've got Ethernet, you've got the asynchronous transfer mode, and frame relay. So if they ask you the question, at what layer of the OSI model does frame relay run at? It's layer 2. The protocols at the top are the protocols that we see as application protocols. And the one protocol that you might have a question about is RIP, which is the Routing Information Protocol. RIP is actually an application, but it's going to utilize what it learned at the network layer. So it actually reaches down to the network layer and pulls that information up to make its decision as to where to send the traffic. So when we take a look at the RIP protocol, it's actually running at the application layer. We talked about the fact that TCP is based on concrete interaction between the protocols and the fact that this is a robust protocol in that we want to be able to, again, have this 3-way handshake that's going on between ourselves and somebody else. So if we lose a packet, that we can send the data in such a way that if we lose the data, we can go ahead and resend this should we need this. One of the reasons that I give you the diagram that I did before we broke for lunch is because if you know how data flows from one side to another, 2 things happen. One, you understand what you need to know to hack this. But if you know how to hack it, then you understand what you need to do to protect that network as well. So you have to understand how the information flows to be able to understand where would you go in to hack this. So TCP/IP is vulnerable to that. We took a look at the data link layer and the fact that at the data link layer we are containing the technologies that can handle addresses, traffic, direction, and security. We talked about the fact that we're looking at MAC addresses on the switch. The switch has a CAM table and it knows which port you're coming out of, what your MAC address is that we're going to, and it's redirecting the traffic through this. Now, let's talk about a couple other devices that we have besides the switch. What was the predecessor to the switch? I'm sorry, I forgot to move over there. Thank you. So here's my workstation. I want to go up to this guy over here. So I'm at A. I want to go up to B. When the data hits the hub, where's it go? Does it also come back down to me? It does. So if you were watching the workstation, you would see the traffic go up, you would see the NIC shut down, and you would see the traffic come right back down to us. This whole thing right here is known as a collision domain. Why? Because if I'm sending out traffic, nobody else gets to use this arena besides me. I'm sending out traffic. Nobody else gets to send out traffic. So the replacement for the hub was a switch. There was, however, a device that bridged the gap between the hub and the switch. What was that? Bridge. Did you like the hint I gave you? I said a bridge the gap. This is a bridge. How does a bridge differ from a switch? Can anybody tell me what a VLAN is? So what? Its own logical network on a switch. So we go into a VLAN to segment our traffic. When switches first came out, they were being transitioned from a bridge over into a switch. I know this because when I first started teaching the Cisco classes, I went and bought myself 10 of the 1900 series switches. And we're doing a VLAN exercise in class, and one of my students goes, well, I don't have VLANs on my switch. I've got bridging groups. The hell's a bridging group? So a bridging group, you have 4 bridging groups on your system. So it's like putting a hub here, in here, and off of each one of these. And the bridge was actually smart. So I got workstation A, B, C, and D. I want to send traffic from A to B. When the traffic enters the hub, where's it go? Down to B and up to the bridge itself. When it reaches the bridge, it says, is the destination address in the same bridging group? And the answer to this one is no. Therefore, it doesn't send it anyplace else. But if I move traffic from A to D, as the traffic comes up here, it's going to get sent down to B. It'll come up to the bridging group. It's going to say, well, nope, it's the destination's in a different bridging group. It's going to blast it to there, and here, and it'll get sent down to C and D. So the bridging group started giving us this idea that we can separate out or segment our traffic by different VLANs, also known as segmented groups. So I could go in and say, I want each one of my departments to be a different VLAN. Now, as we transition over into the switch was great because if I want to send traffic from my workstation here on A up to this workstation here on B, my data can flow up like this. At the same time that's happening, I can have this conversation, this conversation, this conversation, this conversation, and this conversation all at the same time. If I have 24 ports, that's equal to 12 conversations. And if those conversations are running at 100 megs per second, and I want to maintain 100 megs, so it's coming in at 100 megs, it's coming out at 100 megs, and I want it to transition through at 100 megs, then I would have to have 12 times 100, which is 1.2 gigabit. I would have to have a 1.2 gigabit backplane to maintain wire speed going through. If I ordered and went out and bought myself right now a 24 port Cisco switch where all the ports are 100 megabit, guess what the backplane speed is? Exactly 1.2 gigabits. It's not rocket science. It's basic mathematics. Now, any of you ever had a cheap boss? Yeah, you've had one in the back? So your cheap boss comes to you and says, we've got a 24 port switch here. Every single port is filled up. The nice thing about every one of these ports is it's its own collision domain, so I don't have to share bandwidth with anybody. However, with my 24 ports that I have on this switch, they're all filled. Every port is already taken. But tomorrow I've got 5 new people coming into the office. So we need to add 5 more people to my network. And we don't have the money to go buy a new switch. Is there any way that we can go ahead and add another device to my switch to give us access to 5 more people? What device would I add in? Router's not going to give me any more access. Is there something I can go pull out of the old closet and add to this? Oh, God, did you say a hub? God, that sent chills down my spine. Who's the first person you're going to put on the hub? Why? Because you don't like him? Because you want to show him he's cheap? As a field service engineer in San Francisco area, we had a building that was very similar to this room in its shape. Coming right through the middle wall, this side was all salespeople. IT folks were over here. Up above were the owner's offices. And over on the IT side, it's 10 o'clock in the morning, and the window comes a whipping open. And I hear this, "Lefevre, get up here." So I go up the stairs, and I went, "Well, what burr is up your ass today?" And he's looking at me, he's like, "God, can I just get some respect?" I said, "Respect is earned. Earn it, and I'll give it to you." And he goes, "Why is it you're still here?" I said, "Well, you know, I'm the first one here in the morning. But you don't give me a key to the office, so I got to wait till somebody else shows up." So the first thing I do is I walk in, I turn on my computer system, and I go make a pot of coffee. I have 2 cups of coffee. By the time my system's booted up, I can now log in. Once I've logged in, I bring up our program. While it's running, beginning to run, I go make another pot of coffee. I have my 3rd cup of coffee, and now it's 9:30, and I can now contact my client. So I can get on the computer, you know, connect with them, find out what time I'm going to show up at their office. And he's like, "I think I know what your problem is." "What do you tell me my problem was?" "I drank too much coffee." I said, "No, the problem is you're too parsimonious." He looks at me, he gives me this look of cross-eyedness. He goes, "You know, I went to Berkeley," and he's got his degree right here from Berkeley. He said, "I went to Berkeley, and I have no idea what you just said to me." I said, "Well, I did not go to Berkeley. I went to a state university. I paid 1/10 the amount of money you paid for your degree, and I know what parsimonious means. It means you're frugal." And he looks at me and he goes, "Did you just call me cheap?" "No, you just called yourself cheap, but if the shoe fits." And he says, "I'm going to be on vacation next week for the whole week, and I want you out of here every morning by 9 o'clock. I said, "That won't be a problem." So the next week comes and go, I'm out of there every morning by 9 o'clock. Following week comes back, he shows up, it's almost 9 o'clock. That window upstairs comes a whipping open, I hear this, "Lefevre, get up here." So I go upstairs, and I went, apparently the bird did not come out of the place where it was lodged. What seems to be the problem? He's like, "Why is my system taking so long to boot up?" What had I done? What did I do? I switched systems. I took his system downstairs, he's got mine. I said, "Your system had no problems booting up this morning. It booted right up. I got in, got my job done." And it's almost 9 o'clock. I got a meeting over at Kaiser at 9, so I got to go. I think you remember how to hook up your system. Yours is downstairs. That's mine. Careful with it. So I walked downstairs. I expected one of two things to happen to me the next morning. What were those two things? Either fired or new equipment. Which one did I get? New equipment. This is what I had to do to get new equipment. So you start looking at a cheap boss and you ask yourself, do I really want to put a hub out here? One of my students told me that his boss recently did this. What are you doing? You're taking this collision domain, and everybody that's living on these hubs out here are part of their own collision domain. The thing about the switch is every one of these ports is its own collision domain. We don't have to share our bandwidth with anybody else, and that's what a collision domain is. It says that we're sharing our bandwidth with somebody else. So you always want to make sure that you don't have this huge collision domain that we've got. Okay, so let's go back to our slides. So the collision domain is within my layer 2 because I'm sharing my bandwidth. Now, my broadcast domain is a little different. How many of you have kids? When you want your kids to come in for dinner and they're outside playing, what do you do? Stand on your front. What's that? What my dad used to do, he'd stand on the front porch and become the broadcast domain. Hey, get in there! Okay. So that was his way of broadcasting out. So I'm an independent contractor. Gosh darn independent is what most people call us, GDIs that work with the government. So one of the things that we think about as contractors is the fact that we'd love to do some free advertising. If I wanted to do some free advertising and I put my webpage up on the internet and I said I'm just going to broadcast this advertisement to everybody on the internet, wouldn't that be nice? I wouldn't have to pay for this. What would be the problem with that? Not only would I be doing this, everybody in the world would be doing this. If we inundated the internet with free broadcasts going across, what would happen? We'd bring the internet down very quickly. The router does not let the broadcast go through. So the router is the edge of my local network. So I can broadcast within my local network, but the moment that hits the router goes, this broadcast, we don't let broadcasts go through. So it would be very similar to, where's my phone? I can put my phone here. Michael, I don't know your phone number, do I?
No.
You sure about that?
Yes.
I'm going to dial your number right now. So I'm going to dial 1 star 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 star. Every one of your phones is going to ring. If that were the case, if I were able to do that and then finally you're like, how the hell did you get my number? Oh, I just did a broadcast to everybody. What would happen to the phone company if I did this broadcast to everybody? I'd be bringing down the phone company very quickly. So that doesn't work. So don't worry, I won't find your phone number here. So we think about that broadcast domain. We've got to be very careful about where we're sending this broadcast. We talked about a VLAN, a virtual LAN. We're using those VLANs to separate out usually the departments that we live in. We're going to see those coming up in a moment. Additionally, we take a look at wireless access points. Those also run at layer 2 because layer 2 is MAC addresses, and that's what we do with wireless access points is we look at your MAC address. Now, your MAC address is you're not supposed to be there. What are you doing? So it's going to be, I should have put in a a couple hexadecimals. So it is 12 hexadecimal characters. This first portion right here of your MAC address is going to be the manufacturer's ID. This last portion is the unique ID. So the manufacturer goes out to Aaron and Ayana, they pay good money for this, and then they can get you 16 times 16 times 16 times 16 times 16 times 16, or 16,777,216 different addresses on that unique side for their MAC addresses. Okay? So your MAC address is supposed to be unique to your system. And the reason that this becomes real important is something called IPv6. How many of you have played with IPv6? How many of you are hoping to retire before IPv6 gets into... How many of you look at IPv6 and want to run out of the room screaming? That's most people. When we take a look at IPv6, there are 8 blocks. One, two, three, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Were you using my fingers to count with again? Okay, here's what we're doing. This last half of the address is your MAC address. Did I just take out half of the fun of IPv6? Absolutely. Now, what we've done is we've taken this manufacturer's code, kind of split this box right here. So your manufacturer's code goes here. The unique ID goes here. Oh, I have to use that, I guess. So they took this and they split it in half because this is actually your MAC address is 48 bits and this is 64 bits. And to separate this out, they put it in FE here in the middle of this, just to be able to expand this out and be able to drop this into the middle. So that's what we look at here with our last half of the MAC address for IPv6. So when you're looking at your MAC address is really only 48 bits long. When we drop it into the middle of IPv6, we have to split that out and be able to add that in to be able to take a look at that. So we'll see that coming up a little bit later as we take a look at some of the other addresses. We talked about the fact that with switches are taking a look. Oops, sorry, let me move over to your. The switches themselves are looking at the layer 2, so it's tracking our addresses with a MAC address table. So it can relay the broadcast packets to the entire broadcast domain. So as broadcast comes into the switch sends it to everybody. Remember, when it hits the router stops that broadcast from going through. We are vulnerable to MAC address spoofing because it's real easy for us to find out what your MAC address is and to change our MAC address. These are my VLANs. With VLANs, very simple to set up VLANs and to isolate our traffic. So when we take a look at our VLANs, if I am in VLAN 1 and you are in VLAN 1, we can send traffic between us. If I'm in VLAN 1 and you're in VLAN 2, we cannot send traffic between us unless I have a router to route between them, because each one of my VLANs will be a subnet, and remember, routers route between networks or subnets. So if I wanted to be able to do this, I could go ahead and set this up. So as we start taking a look at some of the mechanisms we have within the switch itself, we have ways of securing our ports. We're going to see those coming up a little bit later on. As we move up to the network layer again is looking at your IP addresses. This is going to be over on the router itself. So at the network layer, this is allowing our larger networks. It's going to reduce our congestion because the routing protocols give us this ability to find the fastest, least congested route to be able to route our information through. And we prevent loops from occurring, so we don't want loops from occurring. So why would I want to prevent a loop from occurring? Well, there's a couple reasons that we don't want loops in our system. Let's say that I've got router 1, router 2, router 3, and this is the 100 network. If I'm running a routing protocol, and for an example, I'm just going to use the RIP routing protocol. The routing information protocol says that every 30 seconds, each router is going to send its entire routing table to its neighbor. So every 30 seconds, R3 is going to say, hey, here's my routing table. 30 seconds later, he's going to send that information on to R1. R1 is going to send his entire routing table over to R2. 30 seconds later, R2 is going to pass that on in that direction and also in this direction. So if I think about learning something from R3, R3 told me about this 100 network, and it says if you want to get to the 100 network, you have to come through me, and he's going to tell R2 about this. What is R2 going to do with that information? Is he going to pass it to R1? Absolutely. Is he going to pass it back to R3? What would happen if he said, hey, to get to the 100, you got to come through me. So I'm going to tell you about it. So here he is, and he's going to say, look, I want to get to the 100 network. So you're telling me I can go to the 100 this way. You're going to send that back over to me. I'm going to send this back over to you, and you're going to send it back to me, and you're going to send it. What have we just done? We've built a loop. This would be the same thing, Grant, if you told me a joke yesterday, and I come in today and I go, hey, I got a great joke for you. What would you think of me? Eric, you've lost your mind. I told you that yesterday. And I'd be looking at you going, really? I must be losing it. Oh, hell, you lost a long time ago, Eric. So you start looking at something like this, and this is one of the loops that we put in. It is called, come on, brain. Oh, split horizon. Split horizon says if I have learned, if R3 has sent the information over to me, I cannot send the same information back over here. So if R3 tells me about the 100 network, I'm not allowed to send it back in that direction. I can send it in the opposite direction, no? So that's not a problem. So that would be one of the loops, one of the mechanisms we have for loop protection, okay? Now, in the RIP routing protocol, the maximum number of hops I can have is 15 hops. So if R3 is told that this is no longer available, what R3 can say is, in its routing table, it's going to say the 100 network is 16 hops away. Wait a minute, we don't have 16 hops. In other words, it's an infinite distance away. You'll never get there from here because it no longer exists. So this is called counting to infinity. So that would be one of the other mechanisms that we have for loop protection. Loop protection becomes real important both at the switch level and at the router level so that we end up not crashing that particular system that we have. So as we take a look at that larger network, those switching loops become important to us. So we want to use more intelligent protocols. We want to use the routing protocols. We want to use the logical addresses or the IP addresses that we have. So the routers that we have are there to join two different broadcast domains. So as we saw in the earlier diagram, I had the 1.1.1.1 network over here, and it was connected to a router, and up above that was the 30/30/30/30. Beyond that was the 20/20/20/20. Beyond that was the 200, 200, 200, 200. Each of the routers in there had two networks. So again, what it's doing is it's joining the two networks or the two subnets together. And that's what routers will do for us. So they're giving us this ability to send the traffic across, because as my routers begin to learn about this, as we go back to that, what I had on the board earlier, the R3 is going to tell R2, if you want to get to the 100 network, come to me. R2 will tell R1, if you want to get to the 100 network, come to me. So the way the traffic would flow from the R1 would be, I need to get to the 100. I'm going to pass that information to R2. R2 goes, where's the 100? Oh, it's out of this interface. Then it passes that information to R3, grabs the information from the 100 network it needs and sends it back all the way across to R1. So my routing protocols will take care of this for me. So this is what routers do for us, is that they interconnect all the different routers and all the different networks. But I do have one other caveat in there that can limit the traffic flow, and it's called an access control list. So I can put on an access control list that says, don't allow this network traffic to flow through to this other location. So this would be one of the ways that we can do this. Within the packet itself, it's got a header. We saw that earlier. We saw the source and destination IP addresses, source and destination MAC addresses. We also have something in there called time to live. What is the time to live? Yes, sir.
How long before he dies out?
So wouldn't it be better to name it time to die? A TTD instead of a TTL? So what's the maximum time to live I can have? 255. Every time I go through a router, it will decrement it by 1. So every time I start going through a router, it's going to decrement it by 1. Why would it want to do this? What would happen if I didn't have a time to live and I just simply put a packet up on the internet and said, keep going until you find mama? How long is it going to keep going out there? Forever, because mama doesn't exist. It'll just keep bouncing around. Do you want traffic just bouncing around the internet looking for something? No, we don't want that. We want it to go through so many times and then all of a sudden it's no longer there. That would be the time to live. So we tack on this time to live that says, you know, that should be within 20 hops of here, so we're just going to set the time to live to 20. If you get past 20 hops, you'll be down to 0. Actually, every time we go through a router, we decrement it. So if I start with 20, I get to the first router, we are now at 19. The next router drops it to 18. When I finally get down to 0, it goes, yep, we can't find you. We're going to go ahead and drop the network, drop the traffic. We talked a little earlier about the ping command. Ping is used by ICMP. ICMP is a control and error message protocol. It is part and parcel of IP. It is there to send messages to us that there are issues and problems. This is needed for core network functions. It can also be used as an attack vector to launch attacks against your network. It does provide several different messaging types, the echo request and echo reply, also known as the ping command. It gives us host unreachable, the source squelch that's no longer available, the redirection, the time exceeded, and we pass our router advertisements and solicitations on to other routers through ICMP. So this is my wireless access point. The wireless access points have several different radios in them. The radios are able to connect to the outside world through these antennas that we have. So these are called rubber ducky antennas. These are actually running at 2.4 gigahertz. The flatter antennas that we have on our access points are the 5 gigahertz. So we have the 2.4 gigahertz, which is the most common. This would be for the radios B and G, N and AC. So 5 gigahertz is more expensive. It's a shorter range than the 2.4. The lower the frequency, the greater the range. But you get more throughput with a 5 gigahertz than you do with a 2.4 gigahertz. Not a whole lot more, but you get a little bit more. And the 5 gigahertz has more channels. So the 2.4 gigahertz has 11 channels, at least in the United States, 13 channels in Japan. Whereas the 5 gigahertz has quite a few more than that. The reason that we're concerned about the 2.4 gigahertz more than we are the 5 is because there are only 3 non-overlapping frequencies or channels within the 2.4 gigahertz. The 1, the 6, and the 11 don't overlap with each other. So these are usually the channels of choice that we use when we're setting up our wireless. We also have the 60 gigahertz, high rate but can't pass through walls. Requires a clear line of sight. In most cases, when we take a look at the access points we have running up here, we're in sight of both of these, so it's very easy for us to be able to access these. And no, I haven't hacked them yet. I would not do that. I'm on a military base. I don't want to spend any time in the brig. As we take a look at the antenna types that we have the omnidirectional, which is those little rubber duckies that stand up. Omnidirectional means that the signal goes around the outside. It's being propagated out from that antenna. But we also have directional antennas. We've got the flat patch that can sit next to the wall and put all its power in that direction. Could be a dish-shaped parabolic that's going to be sitting up on top of my building. It could be a Yagi antenna, which is a directional antenna. Or you can have a homemade antenna. What does the homemade antenna use for its housing? A Pringles can. How far can I go with a Pringles can?
8 inches.
Oh, I'm going to be nice. I've seen one go 12 miles. So out in the Midwest, there were some kids that actually had taken a Pringles can, put their antenna inside of it, the foil on the inside, they directed it out, and they were able to get to the access point that was sitting in the rest stop by the highway. I think that's Interstate 40 that goes through there. No, 80? Is it 80? 70? God, I can't remember. It's been too long since I've been there. Anyway, they were able to get 12 miles out of it. So the Pringles can is great. It's called a Cantana. So you can build these yourself. And by the way, sour creams and chives goes the furthest. That's the best antenna to make that out of. As we take a look at network convergence says that we are going to combine things together. So we want to combine our data and our telephony. So voice, video, and data all together. Many of our industrial systems are going to be converged networks. We're going to take a look at some surveillance. We're going to take a look at HVAC. And we're going to take a look at some data storage. So let's begin with voice over IP. As I take a look at voice over IP, I've got the inside of my network over here. And on the right-hand side over here, I've got a thing called a PBX. What is a PBX? This is a private branch exchange. This is what a lot of companies used back in the day for their phone system. Why? Well, they would go out and they would hire up a company that's going to provide them the phone service. So they would say, the hospital I worked up in Maine was given a PBX to use and lease for 10 years at the cost of $1.5 million for 400 phones. Maintenance cost of $250,000 per year. So when we went over to the hospital and met with them, we said, look, we can give you a call manager right up here, the call agent. You're going to own it yourself. You own the phones, you own the call manager. If you want to upgrade it, you can. You don't have to, but you own it. You're not paying a lease like you are over there. So when building your call manager in your internal phone system, you own all this equipment. It comes to the gateway, and the gateway is going to sit there and say, look, we have so much bandwidth on the WAN. Every phone call is going to use up some of the bandwidth. If I get to the point where I have saturated that WAN line with all phone calls and I have no more bandwidth left, my gateway will redirect that call over the public switch telephone network and make us basically pay for that long distance call. So we would rather use the WAN, but if we allow an extra phone call to go through the WAN, it would disrupt every other phone call that's out there. So as we take a look at the choice between a PBX and a call manager, we'd rather have this because we own it. With that, we're going to lease it, and it's going to cost us a lot more money. You can buy into we were able to get the whole hospital set up with 400 Cisco phones and the call manager and new switches for less than $400,000. And they walked away owning that product. So they were very happy with that. When we take a look at industrial control systems, we've got SCADA, we've got the DCSs. We also have things called the PLCs, programmable logic controllers. Does anybody know what Stuxnet is or what Stuxnet was? Grant, what was Stuxnet? It was the Iranian nuclear facility, pretty close to each other, but pretty far away too. What did they do to attack the nuclear facility? It was a hack. They were going after the programmable logic controllers on the centrifuges. So they were speeding up, slowing down, which basically rendered them useless because they need to spin up and keep going to make heavy water, which is what you need to make nuclear fuel. So they had written their programs to go after these industrial control system programmable logic controllers because of their serial numbers. A month and a half ago, I was up in Vermont doing a class for two groups. One of the groups was state government. The other one was a couple of pilots from the Air National Guard. And this was a class on security. And the guys that were working for the state of Vermont were working for an industrial facility that had concerns about these industrial devices that we have. The SCADAs, the large-scale distribution systems, the DCSs, these are processing the process control systems that are sitting on these devices that are stamping out whatever product you're making. The concern is that these are interconnected, they are networked in other words, and there's no level of security on these, which means that the network that's running them, if you could breach the network, you can get in and start making changes to this stuff. You could put in a Stuxnet virus and go after this stuff. So they were asking the questions of how do we protect our network? And I said the first thing that you want to do is protect your building so somebody who's not authorized doesn't get in. The second thing you can do is control access to those devices through locking down the rooms, the hallways, the doors, and then requiring someone to authenticate and authorize before they have access to any of these systems. So we basically were doing things that are a little beyond my knowledge in the way that they do their work, but I was able to go down to their facility at lunchtime and actually see what they had and offer some suggestions to them. So industrial control systems are not designed for security, neither are the PLCs. So you have to do something outside of the box to be able to handle the PLCs that we've got, or the industrial control systems. As we take a look at network storage becomes real important to us. We want to be able to back up our information. We've got several different choices on how we back it up. First one is DAS, which is directly attached storage. I'm going down to the store, I'm going to buy myself a RAID 5 system, I'm going to bring it up and plug it into my laptop, I'm going to back up what I have. What do I want to go with RAID 5? One of the drives dies, I've got a backup. Or I could go with RAID 1, have two drives plugged in at the same time and write to both of them simultaneously. If one drive fails, I still have my data on the other drive. So directly attached storage is one of the ways we can do this. I can do the network attached storage. You will notice in the DAS that the file system is attached to the server, the application server. Whereas in the network attached storage, my file system is on the RAID box. So the RAID box is actually controlling how the data is being stored on the system. So it's actually got its own OS and its ability to format the drive the way that it wants. So network attached storage means I'm buying something like the EMC squared solutions where they're controlling the file system on that RAID box. I can do the storage attached network, which is again just going out and buying a RAID system, and you'll notice that my file system's up on my application servers, and we're replicating those two servers. Should one go down, we are still up and running. We still have that file system on the RAID, so we know where the information is being stored. So one of these solutions is probably going to be what your company is going to use or what you're going to choose to use. It really comes down to who do you want having control of the file system, the RAID box or your network. To me, it's always the network. I want my network controlling what the box does. Okay, so you got some questions here. Order the OSI layers from the bottom to the top. What is the layer we have on the bottom of the OSI model? Physical above that. Data link above that. Network above that. Transport above that. Session above that. Presentation, and I hope you get the last one because it's the last one. Application. So, application from top to bottom, application, presentation, session, transport, network, data link, physical. Okay. What kind of WAP is designed for use with a central WAN controller? So let's talk about WAN just a little bit more. Where is the wireless access point moving to? What sort of technologies do we now have for the wireless access points? It's been an interesting journey over the last 20 years to watch how the access points have been changing. And they've been changing, I think, for the better, because when we take a look at the access points that we have with their little antennas out here, they really don't want me ever touching an access point again. Thank you. Why don't they want me touching the access point? Because if I can touch it, so can anybody else walking in the building. You'll notice the access point's above our ceiling here. How would I get up there? What do I need? I don't need a ladder. I got desks. I can stack those up. Chris Matthews going to walk in, and while he sees me falling off he's like, what are you doing up there? Oh, nothing. Nothing at all. Yeah, I'll go in and plug into an access point just to see what you're doing. So we don't want people going into the access point to actually make any changes to the access point. So what we want instead is something called the wireless LAN controller. So wireless LAN controller can control my access points. I can control, if I've got a small one, I can control up to 6 access points. If I've got the bigger one, I can control up to 100 access points. Okay? I had a student in my class who told me that he needs to know everything about the wireless LAN controller because he's handling a lot of access points. What's a lot of access points, Matt? How many would a lot be? Take it up from there. Take it up from there. Take it up.
5,000.
He was doing a little over 1,200. I said, where do you have 1,200 access points? He said, in my warehouse. Why do you need 12, Grant, why does he need 1,200 access points in his warehouse? Who does he work for? Amazon. Why does Amazon need 1,200 access points in their warehouse? They got robots doing what? Automatically picking up your orders. Oh, you ordered this. Let's grab this and this. And they got little pockets that they drop this in, and they scoot on over, and they unload their pockets, and the person sitting there prints out your ticket, drops any invoice inside of your box along with all the merchandise, and then on the other printer, prints out the label. They put the top on, tape it up, throw the label on there, put it out on the little beltway, and it takes it right out to the UPS truck, and it's on its way. So the wireless LAN controllers he's got are all controlled by the wireless domain server. So wireless domain server can control all the wireless LAN controllers, which then control the access points. So in the Cisco world, we call these lightweight access points because they put on what was called the lightweight operating system. The industry, however, calls them something a little bit different. They call them a thin access point. So your answer to this would be the thin access point. Your next question, what happens to a non-tagged frame on a VLAN trunk? VLANs, we took a look at the way that the packet is set up. We've got the data. Outside of that's the TCP IP. Outside of that's going to be your source IP and destination IP. Outside of that's going to be your source and destination MAC address. Your VLAN information is stuck in there at the MAC layer. We normally tag this with your VLAN information. If it's a non-tagged frame, we also, if we're going to be using non-tagged frames, we're going to have what's called the native VLAN, which is on the trunk, and that's going to be for my non-tagged frames. So the answer to that one's going to be, you're going to be using the native trunk. I have no idea where that answer came from on their slides.
It's not even there. It's not even an answer.
I know it's not. But your answer is it's forwarded to the trunk's native VLAN, so that's going to be answer C. What protocol would an echo request packet use? ICMP. Yep. Which storage option is just a refinement of a traditional file server? Did you say NAS? You'd be correct.
Yeah, that's what I said.
You want to create a point-to-point wireless link between two buildings. Your goal is to keep a strong signal between the two transceivers while minimizing the area in which the eavesdroppers can access network traffic. What antenna style should you use for each? Yagi, why? It is directional, yes. The Yagi is your best choice. Okay, this next section talks about network addressing. We're going to talk about IPv4 addresses and some IPv6 addresses. We're going to talk about network address resolution, so ARP, and we're going to talk about some NATing or network address translation. So let me go ahead and jump up here on this. Let's talk about IPv4 addresses. When IPv4 came out, we never thought we were going to need any more addresses because we never thought the internet was going to be there. So when we take a look here at IPv4, IPv version 4 has 4 octets. An octet has 8 bits in it, so this is going to be 32 bits. If we take a look at any one of these, the choices we have in any one of these will be a 0 or a 1. So I have 2 choices here. 2 choices here, 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 and here. 2, 4, 8, 16, 32, 64, 128, 256. Unlike the way that you were taught to start counting from the time we were 2 years old until we graduated from college, we started counting by saying, oh, 1, 2, 3. No, we don't start with 1. What do we start with? 0. So if I were to start this out and take a look at all of these, actually I'm going to do this over here. So if I take a look at the 4 or 8 bits that I have here, and we start with all zeros, what's my decimal equivalent of that? 0. If I add a 1 to this, I get 0, 0, 0, 0, 0, 0, 0, 1. What's the decimal equivalent? 1. If I add a 1 to this, what do I get?
2.
I don't have a 2.
Oh, 0 or 1.
I get a 0 or a 1. So if I only have a 0 and a 1 available, if I add 2 1s together, I get a 0, and I have to carry the 1. So I get a 1, 0. Does that make sense? That is my decimal equivalence of 2. Now if I add a 1 to this, what do I get? 1, 1. Decimal equivalent is a 3. So over here I've got my zeros in front. Okay, I'm going to add one more 1 to this. What do I get? That's a 0, Eric. 1 plus 1 is 0. Carry the 1. 1 plus 1? 0. Carry the 1. Decimal equivalent? 4. Okay. So what you just said was right here, if I have a 1 in that far right-hand spot, it is a decimal equivalent of 1. If I have a 1 in the second spot, which is right here, you said that decimal equivalent is 2. You said if I have a 1 over here in the third spot, its decimal equivalent is 4. What is happening every time I move to the left? Doubling. So right here I have 8 next to it, 16 next to that, 32 next to that, 64, and finally 128. Okay, so if I said I've got the number 100, how many 128s in 100? None. How many 64s in 100? So if I subtract 64 from that, I get a 36. How many 32s in 36? That leaves 4, so that's a 1. How many 16s in 4? How many 8s in 4? How many 4s in 4? I know who said that. I don't even have to turn around anymore. Okay, there you go. That's how we get the number 100. That's what it is. 0, 1, 1, 0, 0, 1, 0, 0. So my question to you is, what is a 10, 10, 10, 10? What is the decimal equivalent of that? You get a calculator? You can use my fingers, but you'll come up short. A 128, 32, an 8, and a 2. Does that help? $170 is correct. So 128 plus 32 is 160, 168, 170. How easy is binary, moving between binary and decimal? For some, it's very difficult. Okay. With IP version 4, again, I've got 32 bits here. When Aaron and Ionic came up with the first numbering scheme, they decided with IPv4 we need several different classes of addresses. So the first class we had was a Class A address. All of our classes look at one thing and one thing only. That first number we have right here. So your class is only predicated by the first number, not by your subnet mask. So a Class A address is going to go from 0 to 127. So I might have an address such as 100.0.0.0. What is the default subnet mask for a Class A address? Subnet mask. 255.0.0.0. What is 255 in binary? It is all ones. So there are 8 ones, and then it stops, and then it's 24 zeros, my subnet mask. Where the ones stop and the zeros begin, there's a line between it. Everything on the left is called the network. Everything on the right will be the host addresses that we have. So the host, you've got 256 times 256 times 256, which would give you 16,777,216 hosts. a lot of hosts. Your Class B address begins at 128 and goes through 191. An example of this might be 150.150.0.0. You'll notice in a Class A address, they assign the first octet. In the Class B, they assign the first two. So what is my subnet mask for a Class B address? 255.255.0.0. Again, I've got 8 ones here and 8 ones here where the ones stop and the zeros begin. And my subnet mask, we put a line right here. Everything to the left of this is considered my network. Everything to the right would be hosts. So I've got 256 times 256, or 65,536 hosts. Class C addresses begin at 192, go up through 223. An example might be 200.0. What is the default subnet mask for a Class B address? Or Class C, I'm sorry? 255.255.255.0. So I've got 8 ones here, 8 ones here, 8 ones here. So after going through 24 ones, there's a split right here. Everything to the left of that's going to be my network. Everything to the right of that will be hosts. So it tells me that I have 256 host addresses. Now, out of the 256 hosts, how many are usable? 254. The 2 addresses I cannot assign to anything are the very first address, the .0, because that's my network address. I cannot assign the last address, the 255. Why? Because it's my broadcast address. So I have 254 usable. If I were to ask how many hosts can I put on there, the answer is 253, because you mentioned the gateway address, so I'd have to have the gateway in there as well. So let's talk about the Class D address here. Class D address is going to go from 224 through 239, and this is known as multicasting. In a multicast environment, let's talk first about the unicast. What is unicast? Mano a mano, one-on-one. So I'm going to send you traffic, you're going to send me a response. That is a unicast because I've only identified your workstation. If we take a look at a broadcast, that's going to be me sending out traffic to everybody. A multicast is myself sending out traffic to a select group of people. If you're in the front row, you guys are 224.1.1.1. You're in the second row, 224.1.1.2. Third row, 224.1.1.3. Next row back, you're going to be 224.1.1.4. If you're in the far right-hand side of the room, you're 224.1.1.6. Can you be part of 2 different groups? Yes, you're part of the .6 and the .1 multicast groups. So we can have people in select groups. So this is the Class D, and this is why we have multicasting. Finally, we've got the Class E, which is 240 all the way up to 255, and this is known as experimental. When we take a look at an experimental address, you can use these on the inside of your network. You just cannot use them to go across the internet. Okay? So you're allowed to use these internally, but they'll never make it across the internet. Do we have some other private addresses that we want to keep for Class A, Class B, and Class C on the inside of your network? Grant, what do we got? What do we have for the Class A address? Yep. What are the private addresses? So 10.x.x.x. What do we have for the class B that's private? It's going to be 172.16. You were close, but still pretty far away. Through the 172.31.255.255. And finally on a class C for private, 192.168.x.x. The x's you can fill in with any number you want. Okay. So private addresses would be what we use on the internal side of our network before we send them out over the internet. We're going to do a network address translation to a fully routable address. That way we don't have to worry about addresses on the inside. We've got plenty of addresses to play with. Okay? So what do you need to know about this? Well, one of the things to think about here with IPv4 would be Class A only requires the first octet, Class B the first 2 octets, Class C the first 3. So ABC 1, 2, 3 is an easy way to remember that one. When you take a look at the number of addresses that we are given, in this case 256 for a Class C address, is that the smallest group of addresses I can assign to someone? No, I can actually assign smaller groups than that. So one of the reasons that we have a subnet mask, the subnet mask is there to give me one piece of information and one piece of information only, and that is the number of hosts that I have on my network. Okay? Now when we take a look here at the IPv4 addresses that we've got for our 4 octets. How many bits do we have? 32 bits. Sometimes if my subnet mask were to be a 255, 255, 255, 255, it would be called a /32 because I'm looking only at that last specific address that you have. If it's only a Class C address where we have a 255, 255, 255, my subnet mask ends right here. I've gone through 8 plus 8 plus 8, or 24 bits. This happens to be a Class B address. I've gone through a 255, 255. How many bits have I looked at? 16. This would be a /16 if we ended right there. And if I only looked at the 255, I would end right here, be a /8. Now, they're going to ask you a question on the test that's going to freak you out. I'm here to unfreak you. Going to make this really easy for you. I was over in Hawaii doing a class in Honolulu, and I did a study session at night, and the first lieutenant in my class was just freaking out over this, and she said, I was given a question where it said, I have an address with a /27, which is somewhere in here. She said, I got to figure out how many host addresses I have. I went, well, it's really simple. She looked at me and goes, well, you teach this stuff, it better be pretty simple for you. And I said, no, let me show you a very easy way to do this. What the /27 is telling me, if I said, what's the difference, if I said I had a /24 and a /32, what's the difference between the two of these? 8, which tells me that I've got 8 bits in between them. What's the difference between 27 and 32? 5. So if I were to take a look at this last octet, I said this is a /32. I can go back here to 31, 30, 29, 28, /27. How many bits do I have in there? So what is 2 times 2 times 2 times 2 times 2? You can use your fingers. 2, 4, 8, 16, 32. I have 32 hosts. See how easy that was? How many of those are usable? 30. Why? What am I missing? Network and broadcast. So I always have to take 2 away from that. So 32 hosts minus the 2 leaves me 30. I've got 30 usable. Okay? That's how easy it is. What if they said I have a /26? What's that going to do? So what is /32 minus 26? 6. So what is 2 times 2 times 2 times 2 times 2 times 2? 1, 2, 3, 4, 5, 6. Equals? 64. How many of those are usable? 62. That's all you got to do. That's what they're going to ask you.
That's fine until they give you a /6.
They're not going to give it to you. They're going to be in the 4th octet. They're not going to go that far. You come and take my advanced route class, they're going to do that for you. But this is not the advanced route class. They're going to be pretty easy with you. It's going to be in that 4th octet. They're going to probably give you the /27. What if it was a /28? What's /28? What's 32 minus 28? 4. With 4 bits, how many addresses do I have? 16. How many usable? 14. Boom. Done. Next question, please. That's what I want you to do. I want you just to get the question, answer it, and move on. It's going to happen. It is going to happen. Okay, so this is what's in your book. It's showing us the network ID and the host ID. So they're showing us up on the top row a 10 address, which of course is a class A. You will notice that the network ID is blue and the hosts are all green. When you take a look at the next one, it's 172.31. That is the network side of the address. The green side of that in the second line down is going to be 120 and 35. So that's the 3rd octet and 4th octet. The very bottom one is your Class C address, 192.168.100, showing a .54 for the host address. So when we take a look at any addresses, we're going to get the IP address, the subnet mask, the network ID, which is what's my network address, and the host ID. So they're just showing you that in binary, which you don't need to know. We talked about this. We talked about the classes of addresses. We talked about the first octet and what the IP address of that first octet is. We talked about the first bit and how many number of subnets and how many number of hosts that you have for each one of these. So it does show you, of course, on the very far right-hand side, the /8, the /16, the /24. They don't show you the /32 because if I go all the way out to the end, that's a /32 where I'm looking specifically at one address. So let's take a look at some of the other addresses that we have. We've got some specialty addresses out there. We've got the 0000, which can't be assigned. We've got the broadcast address to broadcast everybody, which is 255, 255, 255, 255. We have the loopback address, which uses the entire Class A address of 127.0.0, and then if we put it in a .1, that's your local loopback address. We talked about the private addresses, the 10, the 172.16, and the 192.168. So that's the Class A, Class B, and Class C private addresses. And finally, can anybody tell me what DHCP is used for? DHCP will assign IP addresses to workstations, usually coming out through a switch. So if I cannot get you the IP address from a DHCP server, or it's been sitting there waiting too long waiting for an address, Microsoft will assign an APIPA address, which is just a placeholder. So that's going to start with 169.254. If you see on your workstation it doesn't work and you do an IP config and you see this address, it just tells me that I've lost my connection with DHCP, so try it again. So this next portion talks about IPv6. Why did we move to IPv6? Who do we blame for this? Al Gore? Why not? When we take a look at the IPv6 addresses, you do not have 32 bits, you've got 128 bits. Did we go from oops, not enough to overkill? Kind of, sort of. It has given us this massive address range. It's easier, I think, to configure my networks. It gives us greater efficiencies, enhanced security because it's adding in IPsec on every single one of our connections. There are, however, some compatibility issues with older systems. So let's talk about the IPv6 address. This is a typical address that we would have. So let's talk about this address for a moment. We talked about the fact that the right-hand side of this, the 120 delta, the 7F, this is the manufacturer's code right here. The FFFE was put in the middle as a splitter. The Frank 3 Charlie Echo 85 is the unique identifier for that MAC address. Let's talk about the first part of the address, though. I grew up in Los Angeles, California, Pasadena to be specific. When I pick up my phone in California and I see somebody has dialed my number from the 213 area code, where is 213 coming from? That's Los Angeles. What's 212? New York City. 480? I'm sorry, 408? Chicago. So you start looking at that, and I knew at one time, I knew all of the major cities and what their area code was. So you could actually look at someone who's calling you, and you could look at the area code, and you could immediately say, this call is coming from this location. Welcome to the first block. The 2001 tells me this came from the United States of America. That first block is going to tell me your country code and the continent that you're on. Just like the phone number that I see coming across tells me the area code where you can't do that nowadays because of cell phones. What does the second number in a phone number tell me? It's going to tell me my central office in that 213 area code. So it's going to identify all the central offices that they have there. So that second number is going to tell me your central office. What does the second number, the Delta 18, tell me? It tells me who your ISP is. Now there's supposed to be 4 numbers in there. Why does it say Delta 18? What's missing? The leading 0. Okay, so we can always take out that leading 0. When I take a look at the last portion of your phone number at home, what do those 4 digits point to for your home phone number? So it points to the phone in my house? I have an extension in my house? When the phone call comes into the central office, and let's say that your last 4 digits are 1111, the phone company is going to say, oh, the person who lives on the 1111 circuit needs to be rung up. What do we mean by that? By needs to be rung up? We're going to apply power to your circuit in the form of 120 volts, which is going to cause what to happen on your phone at the other end? Ring, ring. If you have ever had the opportunity to touch those wires when someone's ringing you,
Oh my God. It's only
this explains a lot, gentlemen, a lot. I have 2. My boss decided to do it as a joke. So the moment that we ring you up with 120 volts, the moment you pick that receiver up, it drops your voltage right down to 48 volts. So you can get electrocuted with 48 volts, and all it's going to do, if you have hair on your head, is make it stand up. I mean, if you shave your head, you don't have to worry about that. So the first three numbers that we have, this is telling me which country and continent you're on. This tells me who your ISP is. The next one tells me which customer of the ISP you are. It's very much like your circuit number coming out. This one right here is something that belongs to you. You have 65,536 different combinations of characters, because those are hexadecimal. Are you ever going to have 65,536 different devices at your house or in your possession? Did we just kind of do an overkill for you? Give you way too many things for your house and your kids and all that? We're expecting extended family to live with you, and, you know, grandparents and uncles and aunts and kids and cousins, and, you know, your house will have 65,000 things in it. Now, how many of you can hold up your cell phone right now and show me a picture of your refrigerator? Nobody? Good.
I probably could.
You can?
Yeah.
You have a picture of your refrigerator on your phone?
Yeah.
Like the inside?
No.
Outside?
No. If you have a picture when you look at your phone,
Oh, it's like the background? No.
it is the background, because it means that your phone is connected to your refrigerator and your refrigerator is running your house. This is the new smart refrigerator. So when you bring up your refrigerator on your phone, your refrigerator can turn on and off your lights, your stereo, your coffee maker. The new one, wait for it, is your wireless crock pot. I don't get the wireless crock pot. Anyway,
They're going to run for a long time.
how many people show up at Fort Meade on a daily basis in the way of employees, soldiers, contractors? More than 65,000? Yes? It wouldn't even matter. More than 2 million? 20 million? No? Okay. Could I go to the ISP and say, I would like the first 3 blocks assigned to Fort Meade? Every person here, every device you have is already uniquely identified by what? Your MAC address. So I never have to touch that subnetted area that's blue right there, do I? I don't even need that. I don't need that at home. Why? Because every device I have in my house is uniquely identified by its MAC address. I don't need that blue section. But let me go ahead and give you why we need subnetting, because we do this in my Cisco class. So let me show you the example we came up with. It's going to make subnetting on Class C or IPv6 addresses pretty easy. So with IPv6, what I do in my routing class is we have a couple routers, so R for router, and I got a couple workstations. And my buddy Curtis is also a Cisco instructor, and we were given an edict by Cisco. You will be teaching IPv6 exercises in your class starting next week. So he and I are on the phone, and I went, so where you at? He's like, I'm up in Canada, eh? What part of Canada, eh? Oh, I'm in Vancouver, eh? Like, why do Canadians always put A at the end of everything? He says, I don't have any idea, eh? So we're talking, and I said, we got to come up with a new exercise by next week for Cisco to do IPv6 subnetting. And he went, I hate V6. And I said, I hate it even more. I said, so we need to come up with a very simple address. And he says, okay, eh? I said, what do you want to do? I said, hey, Take it from there. A, Eric, A, :/64. Okay? If you remember, we have 8 blocks. I'm just going to put circles in for the blocks. Okay? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we know that this is a /64 because all the way out here is a 128. Okay? So we're only looking at the first 4 blocks. What do you think the double colon means? Zeros. So what this really is A0, 0, 0. So what is the important part of this? The first 3 parts of this are important. Everything to the right of that line is my subnet mask. What are the choices that I have over there past that red line? What could my gateway address be that's right here? Could it be A001? Could I put a 1 in here? Really? You're doing that? That's what I wanted there. Thank you. 1. Could it be a 1? Could it be anything from 1 to 9? Could it be anything from A through F? Those are the choices. I could put any one of those in there. So I could say my gateway for this is going to be A::A /64. So I just chose that one right there. That one right there. Okay? Well, if this side is A, what do you want to make that? B? That's what we did. We called that one B. Okay, so if this is B::B, that's B0, 0, 0. Anything to the right of this can be somewhere from 1 to 9 or alpha through Frank. What would you like to put in on the other end? Okay. If I got A over here and B here, what do you want to put over here? C. So we said this is going to be C::/ /64. Your choices up here could be anything from 1 to 9, alpha through Frank. What did you want to put for our gateway address up here? Okay? That's what we did. That's how easy it is. You're looking at that 4th block as belonging to you. As long as you don't repeat the 0, it can be any one of these choices. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, or F. Any one of them will be in the same subnet. Okay? That's how easy IPv6 is. The problem we have with IPv6 is nobody uses real basic addressing. They're going to go ahead and give us the addresses that we see up on the screen. So we're looking at these things where we've got the 2001 0 Delta 18 Charlie 34 Delta as the address. We start looking at the block sizes of those going, God, those, especially if you got to go and put those on all the different interfaces throughout your entire network. This is where you start doing copy and paste, copy and paste, copy and paste, copy, 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 paste, 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 and you just get tired of this. So IPv6 is a big leap as far as the number of addresses, but it also gives us a solution out there. So some of the different IPv6 addresses that we have, we're going to take a look at when we get back from break. So we'll see you guys back at 10 after 2.